This video is going to be our second video looking at carboxylic acid derivatives, finishing with acyl chlorides, esters, and a little bit of transesterification. So the last time we looked over a lot of different reactions involving alkyl acid chlorides. One final one involves amines acting as your nucleophile. This mechanism is going to act the exact same way as our earlier ones with our nucleophile, creating a new functional group. This time it will be an amide. So our ammonia is going to act as our nucleophile. It'll come back in, push electrons out onto the oxygen. Since we have a good leaving group, that oxygen can push those electrons right back down, kicking out chlorine. Remember your last step, either having another molecule of ammonia come in or your chlorine to deprotonate your nitrogen. And your last step, you're left with your neutral amide. One little thing about this mechanism, tertiary amines, since they do not have an available proton to abstract, they are not going to be able to act as a nucleophile here. So looking at primary, secondary, and of course ammonia. The next functional group we're going to talk about, or carboxylic acid derivative, will be anhydrides. For nomenclature, you're just going to treat them like carboxylic acids, except the acid portion is going to be replaced with the anhydride. So you have a 1,2-benzene dicarboxylic anhydride. We would name that just an acid if we didn't have that interconnecting oxygen. Here we have an acetic propanoic anhydride, and again naming your groups with alphabetical order being your tiebreaker. Heptanoic anhydride, you have your branching change on both sides. Traditionally, anhydrides are equal on the same length on both sides, so the upper one on the right is a mixed anhydride, meaning your lengths are different. Those are less common. But traditionally, you'll have the same chain on both sides. So heptanoic tells you need a 7-carbon chain. Anhydrides undergo the same reactions as acid chlorides. So same thing, it doesn't matter what our nucleophile is. You can pick any one of the other reactions we talked about in the last video. The only difference is your leaving group is your carboxylate. So your nucleophile will come in, electrons get pushed back onto the oxygen, pushed back down, creating your leaving group. And remember to deprotonate your nucleophile. It can be with your solvent, or it can be from the leaving group carboxylate ion you just created. So if we have an anhydride with water or an anhydride with an alcohol, both times you're going to see that our oxygen is going to act as our nucleophile, and we're going to generate a carboxylic acid. If we use an alcohol, we will generate an ester. Remember, acids will also be generated from your leaving group, picking up the available proton from your nucleophile. And colors, I think, really help illustrate that here. Cyclic anhydrides also react the same way, so remember that our solvent can come in. Since it's a symmetrical anhydride, doesn't matter which oxygen you attack. Know that your acid, your original anhydride oxygen, is going to pick up a proton, and your nucleophile having an ester on the other side is your nucleophile. So from a practical standpoint, these are very good intermediates because they're a little bit less reactive than acid chloride, so you do see these being utilized more in a laboratory setting. For your synthesis problems, feel free to use acid chlorides or anhydrides. Esters are the last functional group we'll talk about in this video. So esters nomenclature, your IC ending for carboxylate is going to turn to OAT or O8. So here, same thing, you're going to name the chain that's attached to both carbons or both oxygens in your ester. So you have a 2-methylpropyl propanoate. Remember, we have 3 carbons on that chain, and the ester, you're naming your substituent off the oxygen at the front. For our ring, methyl 2-amino benzoate, so we know we have a methyl coming off there. There's also a 2-amino benzoate, so imagine if that was just an acid, 2-amino benzoate, or 2-amino benzoic acid. All we're doing is changing that first part. 3-methylbutyl pentanoate. Pentanoate is going to be your base chain where your ester is, and then you're working on your 3-methylbutyl, so it's just a butyl off of that oxygen and a methyl at the 3 position. Remember here that your numbering starts closest to the oxygen. It doesn't matter about making your substituent smaller. It has to be relative to the oxygen in your ester. Ester synthesis, this is the main way these are made. Diazomethane acts as a carbon source. So you have a carboxylic acid with diazomethane, you can make your ester. This is a very high yield reaction, partly because we're generating nitrogen gas, so it's irreversible. Only one thing can happen. Mechanism, this first step is resonance forms of diazomethane. For the first part, you really need to know that if you see a CH2- or any type of anion, it's going to act as a strong base. Remember, we're also starting with a carboxylic acid, so that proton is going to be easy to take off. At that point, you generate your carboxylate anion. You still have a molecule with a charge with your methyl diazonium ion. So your carboxylate ion can act as a nucleophile and undergo an SN2 reaction where it takes the methyl group off, generating your nitrogen gas and your desired ester. Reactions, the same thing as before. Anything we react with water or a hydrolysis reaction, you're going to get a carboxylic acid. This is going to be the reverse of esterification. So remember on the last video we talked about esterification being a way to generate esters from carboxylic acids. Here, this is going to be basic catalyzed, so we'll generate our OH. Here, that's going to serve as the OH that's eventually going to become part of our carboxylic acid. So we'll see our OH act as a nucleophile, push electrons out onto the oxygen, push it back down in order to kick out our leaving group. From there, remember we've created an anion leaving group that's going to have the ability to take off that proton. Again, in this case, we've generated a carboxylic acid, so that proton is going to be pretty easy to abstract. So here you would need to follow up with acid workup just to provide the hydrogen for your acid to stay protonated. Transesterification is a process that takes place where you're essentially changing the R group for your ester. These are often done with an excess of alcohol or whatever alcohol R group you want to add to your ester. So you can see in the top we're trading an R prime for an R double prime. Mechanism for this. It's going to be very similar to our other mechanisms where we had an alcohol acting as a nucleophile. It's not a great nucleophile, so our first step is going to be protonating that oxygen. At this point, our alcohol can come in. For these, remember that you're always going to have to deprotonate your first step there to make your neutral tetrahedral intermediate. At this point, you should see that we're going to make a new ester. So our new R group is going to not be a methyl. It could be anything other than that. But from here, we're going to have to kick out our original OCH3 group. It's not a great leaving group, and we're operating under acidic conditions, so it can't leave on its own. It needs to get protonated first. In that case, once it's protonated, we can have our electrons from our oxygen drop down, give us our carbonyl. Last step again will be deprotonating that, and now we are left with our new ester. Same reactions can happen with opening rings. The top one's just an example of looking at how our functional group changes. So if we had an ethyl ester, we can react it with methanol to make a methyl ester. Transesterification, the same thing. We can have our alcohol act as our nucleophile, come in, kick out the O-, that'll eventually pick up a proton, but you can see that our green oxygen, our alcohol on the left, is the oxygen from the original ester, and we've added a longer chain onto our ester with the bromine on the end. That's it for this video.